Hi, we are from Expert Team A. We'll be introducing cost accounting and capital costs. So allow me to introduce my expert team members, which is DT7 and DT15. So members from DT7 are Muhammad Daniel Ashraf, Badru Moaz, Noor Farah Jasmine, Hong Xing Yun, and me, Tan Shen Ni. Whereas the members from DT15, which is Danish, Crystal, Muhammad Kir, Chia Hui Singh, and also Shankari. Before we start our topic, let me ask you one question. Have you ever wondered why business sometimes hesitate before investing in a new project even if it looks profitable? That's because behind every major decision lies a very careful evaluation of cost accounting and capital costs. And today, we're going to discover how these two concepts guide smart financial choices. So, in our video, we will be covering what is Chemical Engineering Cost Index, what is the capital investment cost and how do we define it, and how we conduct the estimation of the total capital investment, and what is the purchase cost of the most widely used and the other chemical processing equipment, and what are the differences between both of the calculations. These answers will be revealed until the end of the video.
First, let's talk about the cost index. Cost index is the ratio of cost of the product today to the cost of the same product in the past. So basically, there are four common methods that used by the chemical engineering. The first one is the Chemical Engineering Plant Cost Index, which can almost used for all chemical processing industry. The Marshall and Swift Equipment Cost Index, which is useful for process industry, which average equipment cost index. The Nelson Farah Refinery Construction Cost Index, which is for the petroleum industry, and lastly is used for construction and civil engineering project, which is the Engineering News Record Construction Cost Index. In our slide, we are going to focus on the Chemical Engineering Plant Cost Index. It is used to track the price changes over time for plant constructions, equipment, and operating costs. It is to adjust the historical cost data to present-day values. The formula is equal to the base cost, which is the reference cost level, multiplied with the index value for the year that we want to estimate the cost in, divided by the index value for the year of the base cost. For the index value that been used in the formula, you can get it from the graph or from the table, or you can click the link in the right bottom corner there to access the graph of the index value. Let's talk about an example. If a chemical plant cost 10 million to build in 2008 and the CE index for 2008 was 575 and for the CE index is 813 at 2022, so you can adjust the cost at 2022 by using the formula. So the base cost will be 10 million, which is in 2008, multiply with the index value at 2022, which is 813, divided by the index value at 2008, which is 575, and get the cost is equal to 40 million. Next is on the economy of scale and system factor. It is to estimate how the capital cost of a plant changes with the capacity of the plant. So this is the formula, and the M is the exponent, which is the average value is close to 0.6. And if the capacity is double, the 0.6 exponent will give a 52% increase in the cost. Example, total depreciable capital investment for a plant to produce 1,250 tons per day of ammonia was 140 million in 1990. So we can estimate the investment cost for a 2,500 tons per day of ammonia in 2013. So the cost will be equal to 140 million in 1990 multiplied with the capacity of the plant in 2013, which is 2,500 tons per day of ammonia, divided by the capacity of plant at 1,250 tons per day of ammonia, power 0.6, which is equal to the M. And since there is a changes of the year, so we need to multiply with the 567, which is the index value at 2013, divided by the 358, the index value in 1919. So the cost will be equal to 337 million.
Capital investment cost is a total expenditure required to design, purchase, install and prepare the equipment for the actual operation in chemical plant or the industrial facilities. Installation costs are considered a direct cost, and they are typically fall under two main categories, which is the installation materials and the direct labor. Let's start with the installation materials. This excludes everything needed to physically install the equipment and make it functional, such as concrete for the equipment, foundation, steel and structural support, piping, instrumentation and controllers, lighting and the electrical material, as well as the installation and the paint protection, and also the safety compliance. Next, we have the direct labor, which is the human effort involved in the installation process. They exclude the laborers and the technician responsible for the placing the equipment in the correct position, installing and connecting the piping, and also handling on the site fields such as the welding, cabling, and also installation. Indirect costs are additional expenses that are not directly tied to the material or the labor used to install the equipment, but they are essential for the overall success of the project. First, we have the freight, insurance and taxes, which is typically about around 8% of the total equipment. This includes the transportation of equipment from the supplier to the plant site, insurance coverage during transit, and any applicable taxes. This to ensure the equipment arrives safely and legally ready for the installation. Second, there are construction overhead. These are general costs involved in managing the construction site, such as fringe benefit and burden costs, salaries and benefit for the supervisor, temporary facilities, site cleanup and security during the construction. And third, we have to consider the contractors' engineering expenses, which is cover the cost technical professionals such as project and process engineer, designer, the procurement team, and also the home office support. And finally, we have the site preparation and services, which is a rate about 4 to 20% depending on the condition of the site. This includes like a land grading, soil testing, drainage, and setting up the utility services such as water, electricity, and the access road. There are several other investment costs that must be factored into the total installation cost. First, we have the spares, total storage tank, search vessel, catalyst, and also the computer system. These items support the ongoing operation and maintenance of the facility. For example, spares ensure the quick replacement on the worn-out parts. Storage tank and the search vessel manage the fluid flow and inventory. Catalysts are critical for the chemical reaction in many processes, and the computer system handling the process control, monitoring, and safety automation. Next, there are allocated costs for the utilities and supporting facilities like boilers, cooling towers, water treatment system, and the waste management. These are not directly contribute to the production, but they are absolutely necessary for the product plant to operate smoothly and safely. We need to also consider a few percentage-based costs. Contingency contractor fees typically are 80% of the total cost. This covers the unexpected expenses and fee for the general contractor. Land cost usually about 2%, which is varies based on the location, but must be accounted for. Next is the royalty, also about 2%, which is applied when the proprietary technology, patents, or the processes are used under a license. Lastly, we have started cost, which is can range widely about 2 to 30% depending on the complexity of the processes. This table shows the components of the total capital investment. It starts with the bare model cost for the equipment, machinery, spares, storage, catalyst, and the control system, summed up as a total bare model investment. Then we add a site preparation, service, facilities, and the utilities allocation for the direct permanent investment. Contingency and fees give a total depreciable capitals. Finally, we include the land, royalties, startups, and the working capital cost to get the total capital investment. This table shows the allocated capital cost for the utility plan based on the size. It covers the steam, electricity, cooling water, processed water, and the refrigeration. Each utility has a formula which is a cost allocation is equal to the constant time size factor of S to a power, used to estimate the cost. Next, we have the bare model factor, which is calculated by dividing the bare model cost by the equipment FOB purchase cost. Lastly, to estimate the total investment at a specific site, we multiply multiply the total permanent investment by the investment side factor to get the corrected total permanent investment. This is an example of the capital investment estimate for ammonia plant producing 1 billion pounds per year based on the US Midwest. The processes use various equipment like heat exchangers, reactor, compressor and separator, mostly made of the carbon steel. Table 16.14 show the bare module cost calculated using the FOB cost times the bare module factor. The total bare module cost is 138 million USD based on a purchase cost of 40 million USD multiplied by the overall installation factor of 3.452, reflecting the high pressure of gas phase operation. Step-by-step calculation for the capital investment cost. Step 1. Calculate the total FOB purchase cost from this passage. The total FOB purchase cost of the on-site processor equipment is 40.01 million USD. So the total CP is 40.01 million. Step 2. Apply the bare module installation factor to get the total CBM. From this passage, installation cost boosts this amount by a factor of 3.452. Formula use CBM is equal to CP times to the CF. You see CBM is a cost bare module, CP is a cost purchase and CF is a cost factor. CBM is equal to 40.01 times to 3.452 is equal to 138.12 million USD. So the total bare module cost CBM is 138.12 million USD. Now let's move into the step 3, additional bare module cost. These are the standard adds-on based on the industrial practices and calculated as a percentage of the total bare module cost, which is 138.12 million USD. Spare are estimated at about of 0.58%, giving us 0.66 million. Storage and the surge tank typically at 0.41% or 0.57 million. Initial catalyst charge is about 0.46%, totaling of 0.63 million. Adding this up to the bare module cost, giving a subtotal of 139.98 million USD. Now, step 4, direct site cost. Site preparation is estimated at 4.20 million, roughly about 3% of CBM. This covers groundwork, grading, and basic construction prep. Service facility including the roads, building, and the general infrastructure at 2.09 million. And allocate utility costs for steam power and cooling water and so on are calculated at 19.61 million. Altogether, this bring out the direct permanent investment to a solid 165.88 million USD. Step 5. Adding the contingency and the contractor fees. This step account for the unexpected costs during the construction like design changes, inflation, or the contractor margin. We use 18% of the direct permanent investment, which is standard value for moderate complex chemical plant. To find the contingency and contractor fees, which is equal to 0.18 times to 165.88, which is equal to 29.86 million USD. This brings the total depreciable capital, which is TDC, to the 165.88 plus 29.86, which is equal to 195.74 million USD. Step 6. Adding the land and startup costs. Now, we include the costs that are not depreciated. Land costs are assumed at the 2% of TDC, which is equal to 0.02 times with 195.74, which is equal to 3.91 million USD. Startup cost is 8% of the TDC, covering the commissioning, testing, and the training. So the startup is equal to 0.08 times to 195.74, which is equal to 15.63 million USD. These percentages are typically for the large-scale chemical plant based on the reference like Titan ETL. So the total permanent investment TPIs become 195.74 plus 3.91 plus 15.63, which is equal to 215.28 million USD. Step 7. Adding the working capital. Working capital refers to the fund required for day-to-day operation once a plant starts, covering the raw material, utilities, labor, and inventory before the revenue begin flowing. Based on industry standard, working capital is typically estimated at 6% of the total permanent investment. Working capital is equal to 0.06 times 215.28 is equal to 12.80 million USD. So finally, we calculate the total capital investment, which is 215.28 plus 12.80, which is equal to 228.08 million USD. This concludes that the step-by-step capital investment estimation from the equipment cost all the way to the working capital required to the launch and run the facility efficiently.
Next, I will present about the estimation of total capital investment. There are 4 categories. For the first one is order of magnitude estimate based on bench scale laboratory data sufficient to determine the type of equipment and its arrangement to convert the fixed stock to product. The second one is study estimate based on a preliminary process design. The third one is preliminary estimate based on detailed process design studies leading to an optimized process design. The last one is definitive estimate based on a detailed plan design including detailed drawing and cost estimate sufficient to apply cost accounting. There are 3 methods, and the first method is order of magnitude estimate based on the method of Hill 1956, and this method is used in the early feasibility stage where limited information is available. It is particularly useful for low-pressure petrochemical plants where it has an accuracy of approximately 50%, and it is to produce the estimate a production rate in pounds per year and a flow sheet showing the gas compressors, reactors, and separation equipment required. Heat exchangers and liquid pumps are not considered in making the and it is the important factor in making the estimate is the design pressure of each major piece of equipment if it is greater than 100 psi. The method proceeds as follows based on year 2006 Marshall and Swift process industry average cost index of 1,365, a best production rate of 10 million IB per year for the main product, carbon steel construction, and a design pressure of less than 100 psi. Next, I will explain about the calculation flowchart and equation for method 1. Step 1 is compute a production rate factor FPR using the 6/10 rule by using the following equation. Step 2 is using a process flow sheet calculate from the following equation a module cost CM for delivering and setting in place each major piece of equipment except low compression ratio recycle compressors and blowers, heat exchangers, flash and reflux drums or liquid pumps. And CM can be calculated by using the following equation, where FM is a material factor, and the material factor can refer to this table. After that, sum the values of CM, multiply the sum by the factor FPI to account for piping, instrumentation and automatic controls and indirect costs, and update with the current MS cost index, giving the total bare module investment CTBM, and the CTBM can be calculated by using the following equation, where the factor FPI depends on whether the plant processes solids, fluids, or a mixture of the two. Then, in step 4 is to obtain a direct permanent investment CDPI multiply CTBM by the following factors to account for site operation, service facilities, utility plants and related facilities, and CDPI can be calculated by using the equation. And F1 and F2 can refer to the table below. And then obtain the total permanent investment and the total capital investment by the following equations, where a large contingency of 40% is used because of the approximate nature of the capital cost estimate, and the cost of land, royalties, and plant startup are assumed to add on additional 10%. Working capital is taken as 50% of the total permanent investment. And this is the example of calculation by using method 1. And this is the equation that made an order of magnitude estimate of the total capital investment as of early 2007 with MS equal to 1,400 to produce benzene according to Tubin hydrodealkylation process shown in the figure. Assume an overall conversion of Tubin to benzene of 95% and 330 days of operation per year. Also assume the backup gas enters at the desired pressure and a clear adsorption treater must be added to the flow sheet after the stabilizer. The treater removes contaminants that will prevent the benzene product from meeting specifications. In addition, in order for the reactor to handle the high temperature, it must have a brick lining on the inside, so take a material factor of FM equal to 1.5. Otherwise, all other major equipment is constructed of carbon steel. The plant will be constructed outdoors with major addition to existing facilities. This is the solution for the question. We do it step by step. For the step 1,
we need to multiply 330 multiplied with 24 because one day have 24 hours to obtain the operation day. Next, we need to calculate the annual benzene production rate by multiplying the conversion 0.95, multiply with feed rate, multiply with molecular weight of benzene, and multiply with operation day to obtain 161 million IB per year. And this value insert to the equation to obtain the FPR. Next, step 2. We need to identify the flow sheet have what equipments. The flow sheet includes one reactor operating at 570 psia, 3 distillation columns operating at pressure less than 100 psia, 1 compressor operating at 570 psia, and 1 adsorption tower assumed to operate at less than 100 psia. Therefore, the sum of the CM value is as following. Note that there are difference of less than 100 psia and bigger than 100 psia. Next, step 3. We need to calculate the total bare module investment CTBM. And this process is as fluid handling process, so we need to use the 2.15 and we insert the MS index and calculate for the CTBM. After that, we note that this question is about outdoor construction and major addition to existing facilities. And we take the value from the table and insert to the formula to obtain the CDPI. And after that, we also can obtain CTPI and CTCI. And this is how the method 1 estimation do. Next is method 2. Study estimate based on the overall factor method of Lang 1947A, B, and 1948. And this method is used during conceptual design where major equipment has been identified. This method requires a process design complete with a mass and energy balance as well as equipment sizing including heat exchangers and pumps. And accuracy is improved to plus minus 35%. And to apply this method, the FOB purchase cost of each piece of major equipment must be estimated. And this is a calculation flowchart and equation for method 2. Step 1. From the process design, prepare an equipment list giving the equipment title, label, size, material of construction, design temperature, and design pressure. And step 2. Using the data in step 1 with FOB equipment cost data, add to the equipment list the cost and the corresponding cost index of the cost data. Update the cost data to the current cost index, sum the updated purchase cost to obtain the total FOB purchase cost CP, and multiply by 1.05 to account for delivery of the equipment to the plant site. Then, multiply the result by an appropriate Lang factor to obtain the total permanent investment CTPI or the total capital investment CTCI. And these two tables are useful during doing the method 2. And the first one table is about the original and recommended Lang factor, while for the second picture is about the breakdown of Lang factors. And this is the example of calculation by using method 2. The question is, use the Lang factor method to estimate the total capital investment as of the year 2006, MS equal to 1,365 to produce cyclohexane according to the benzene hydrogenation process shown in figure. However, the mega hydrogen feed is not available at 335 psia but at 75 psia. Therefore, a feed gas compressor K2 has been added. Also, 2 heat exchangers have been added. Reactor effluent stream S7 now enters new exchanger H2, which cool the effluent to 260 Fahrenheit by producing 10 psig steam from boiler feed water. The effluent leaves H2 as stream S7A and enters new exchanger H3, where it is heat exchanged with the feed benzene, heating the benzene to 235 Fahrenheit, while being cooled to 201 Fahrenheit and leaving as stream S7B, which now enters existing exchanger H1. The process design has been completed, with the equipment size in the equipment list of table 16.18. Also included in table 16.18 are estimate of the FOB purchase cost in the year 1977. All equipment is fabricated from carbon steel. And this, the equipment list, include the FOB purchase cost of the equation that required for the method 2. And after that, just insert the value that calculated and also the MS index to the equation to calculate for the total capital investment. And this is the last method, which is method 3, preliminary estimate as on the individual factors method of Book 3, 1969-1974. And this method is used in preliminary design when detailed equipment specs are available. And this accuracy is improved to perhaps plus minus 20%. The Guthrie method can recognize that the foundation, supporting structure and ladders, as well as electrical installation and pen will cost the same irrespective of the materials of the construction used for equipment or whether the equipment is designed to withstand high pressure. The equation for the total capital investment by Guthrie method is as following, and the equation does not account for royalties or plant startup. The total base module cost TBM refer to the summation of bare module cost for all items of process equipment, including fabricated equipment, process machinery, spares, storage tank, search tank, and computer and software. And this is the calculation flowchart and equation for method 3. Step 1. Prepare an equipment list, giving the equipment title, label, size, material of construction, design temperature, and design pressure. And step 2. Using the data in step 1 with FOB equipment purchase cost data, add to the equipment list the cost, CPB, and the corresponding cost index of the cost data. And then update the cost data to the current cost index. For each piece of equipment, determine the bare module cost using bare module factors FBM by using the following equation. FBM is bare module factor, FD is equipment design factor, FP is pressure factor, while FM is material factor. Then the next step is obtain the total bare module cost by summing the bare module cost of the process equipment and estimate the total permanent investment. And this is the example of calculation by using method 3. The best FOB purchase cost for a fabricated vertical pressure vessel, 6 feet in inside diameter and 100 feet in height, made of carbon steel for a design pressure of not greater than 50 psig, is given as 102,000 as of 1995 CE index equal to 381. Calculate the bare module cost for the year 2006 CE index equal to 500. If the vessel is made of 316 flat stainless steel for a design pressure of 200 psig. For this condition, Guthrie give FBM equal to 4.16, FD equal to 1, FP equal to 1.55, and FM equal to 2.6. And by using the equation, can calculate the CBM. We insert the 500 as I and 381 as IB and substitute all of the value in the equation to calculate for the CBM.
Okay, so now I will continue with the purchase cost of chemical processing equipment. Purchase cost refers to the base price of equipment as delivered to the plant, not including installation or auxiliary services. Equipment costs are usually estimated using empirical equations that relate equipment cost to size, adjusted by a cost index, which is CE index. Costs are typically based on CE index of the year 2013, which is 567, adjusted for current year by using this formula, which is the current equipment cost equals to the base equipment cost times with CE current divided by 567. Next, there are two types of equipment which are most widely used: process equipment and also other chemical processing equipment. The examples for the most widely used are pump and electric motors, fans, blowers and compressors, heat exchangers, fire heaters, pressure vessel, distillation, adsorption and also stripping towers. While for the other chemical processing equipment, the examples are dryers, crystallizers, evaporators, mixers or agitators, extractors, turbine or gas drives, solids handling system and also storage tanks. Now I will continue with the cost estimation equation, where the general form used is Cp equals to A times S to the power of B, where the Cp is the purchase cost, S is the size factor, A and B is the empirical constants from table 16.32 in the page 481 to 485 in the textbook. And for some equipment, logarithmic or exponential models are used instead of this equation. So this is the table 16.3 tool that will be used to calculate the purchase cost of other chemical processing equipment. So for the material factor adjustment, it will be used to estimate costs for different construction materials, and this factor will be applied in this correction formula, which is the final purchase cost equals to the base purchase cost times with material factor. Okay, so now let's move on how to estimate equipment purchase cost. So step 1 is to identify what the equipment that will be used for, the required capacity and also operating conditions. Step 2 is to choose the appropriate equipment from the list in table 16.32 based on your process. On step 3, based on equipment type, we will have to calculate the correct sizing parameter, for example volume, area, horsepower, and also use heuristics if needed. For step 4, we will be applying the purchase cost equation for the equipment, which is purchase cost equals to A times S to the power of B. Next, for step 5, we will have to multiply the base cost by a material multiplier if the equipment is not made of carbon steel. And then for step 6, update the cost to today's value by using this formula, which is the current equipment cost equals to the base equipment cost times with CE current divided by 567, which is the CE index of year 2013. And then the last step for this calculation is the result is your estimated FOB purchase cost for the equipment.
So for the example part, we'll be introducing two examples, which is first one will be focusing on the distillation column calculation. So can refer back to the example 16.13, which is on page 468. So it got provide with a few information such as the number of sieve trays, the value of the inside diameter, the tangent to tangent length, the operating conditions, and also its temperature, and then the material of construction and the barometric pressure. Using this given information, we need to estimate the purchase cost of the distillation column at the CE index of 600. So there will be two assumptions. One is the wall of thickness of 1.25 inch, and then another one is the CE index of 600. So first, we need to use the first equation, which is to find the design pressure. But first, we need to find the operating pressure first, as the barometric pressure also given as well. So by minusing the operating pressure given with the barometric pressure, we obtain the finalized operating pressure, and then we use it to find the design pressure. So we obtain 123. Next, we need to find the value of the TP, which is the wall thickness in inches to withstand the internal pressure. And then by using this temperature table with the suitable maximum allowable stress, we can substitute the values inside this equation and then obtain the value of TP. And then for TW is the necessary thickness in inches to withstand the wind load or the earthquake at the bottom of the column. So by substituting the values of the outer diameter of the vessel and also the tangent to tangent vessel height in inches, we'll be also obtaining the value of TW. So next, we need to find the W, which is the weight, using the values obtained just now. And then after obtaining the values of the W, we can use this W to find the value of CV and also CPL. After obtaining the value of CV and also CPL, we can obtain the first value of the purchase cost, but however, we still need to add up with the cost of the 100 sieve trays. So we still need to calculate the value of CVT and also the CT as well. And then after obtaining the CT, we can add it up with the CP to obtain the final value of the total purchase cost. And this one is the second example, which is be focusing on the whole system calculation, which is example 16.16 in page 475. So there are a few assumptions made as well, such as the fabrication from stainless steels with a material factor of 2 for the ratio of stainless steel cost into the carbon steel cost, CE index of 567, and then the whole system consisting of 2 long tube vertical evaporators, a draft tube vacuum crystallizer, a rotary drum vacuum filter, and a direct heat rotary dryer. Also, there are another 3 pumps and also 1 heat exchanger. So I'm going to explain it into 2 parts. First one is the most widely used equipment, and then another one is the other processing equipment. So I'm going to explain about the other processing equipment first. So there will be 5 equipments, which is 2 evaporators, 1 crystallizer, filter, and also dryer, along with the types and also its size factor. So using the table of 16.32 to find the exact equation along with the equipment, and then substitute the value of the size factor into the FOB purchase cost equation, we can obtain the value in the carbon steel first. And then for the stainless steel, we just need to multiply with the factor of 2. As I mentioned in the assumption just now, we need to use the material factor of 2 if for the stainless steel case. So the calculation for the FOB for carbon steel and also the stainless steel for the other processing equipment has been done. Next, I'm going to explain about the most widely used equipment. So the first one is the pump. So the pump, we just need to use this equation, which is FP multiplied with Fn and also CB. And then FP, we can use the table that I present at here right now, and then Fm and also the CB using this equation, along with, and then substitute with the size factor, and then we can obtain the value of CP. And then another for most widely used equipment is the heat exchanger for this case. So for this case, we'll be using CP equals to FP multiplied with Fn multiplied with FL multiplied with CB. But however, the value of CB and the equation for CB just for using for 4 types of heat exchangers only. It can be different for different types of heat exchangers as well. For this case will be floating head, fixed head, U-tube, and also kettle vaporizer. Let's say it's got other heat exchangers that is not involved in these 4 types of heat exchangers as well. There is still other equations of CB in the textbook as well. You may refer it after this, and then after substitute the values of P, the A, and then the small a and the big A, and also the B, and so on, etc. After substituting all of the values inside this equation, we can obtain the value of CP for this heat exchanger. And then after that, since it's for the whole system calculation, right, so we need to add it up all, including the pump, the heat exchanger, and also for the other processing equipment, to obtain the final FOB purchase cost for the whole system for this example. So that's the end of our pure teaching video. So feel free to drop out your questions in the e-learning forum, and we will be answering your questions as soon as possible. And hope you guys will enjoy our video and have a clear understanding of cost accounting and also how to calculate the capital cost as well. So thank you and see you soon!